Hi, everyone. Welcome. My name is Henrik Engström. I'm a senior software engineer at Lightbend. I'm going to be presenting monitoring reactive microservices today. Oh, man. So first, a little bit about who I am. This is not who I am. It's my first computer. It's a ABC80, advanced basic computer for the 80s. It had a 4 megahertz, 8-bit processor with 16K RAM. Those were the days, right? I've been a professional developer since 1998, and I worked as a consultant to 2011 when I joined TypeSafe, which is now Lightbend. I've been working with monitoring-related projects for about 4 years, and I'm currently part of the Lightbend telemetry team. Lightbend, then. How many of you have heard about Lightbend before? Many of you. Okay, so we're behind Scala and I can play and log. I'm not going to go through that. Let's save that for someone else. So the agenda today is, the title was Monitoring Reactive Microservices. So first I want to explain to you what traditional and reactive systems are. And then microservices, just a couple of slides. I know you're bored about microservices. And then we're going to talk about monitoring and monitoring different types of systems. Some challenges and mitigations for monitoring. We're going to look a little bit into the future. And finally, I'm going to talk about our solution that's called Cinnamon or Lightbend Telemetry. And if there's time, I'm also going to show you a demo. So traditional and reactive systems. It's 2017, and we still use synchronous local and remote calls. We're building our apps as single machine apps. Scaling is an afterthought, and we use non-resilient approaches. So the result of this is, as you know, brittle, non-scaling applications. And this is very similar to when I started in 98. Microsoft delivered the N-tier architecture. There were Java applets, servlets, J2E, Spring, which resulted in Spring Hibernate. And that's basically where a whole lot of Java developers are today, this Spring Hibernate domain. So how can we improve? The picture to the left there is a description of JMS, and JMS was introduced June 2006, 2001, so that's how long it's been available. And the modern version today, of course, is Kafka, if you could call it that. And the thing on the right there are two things in one picture. I'm really proud of this picture because the movie, of course, is Back to the Future, and Michael J. Fox and Christopher Lloyd are actors. So it's futurists and actors in one picture. Really proud. These are two approaches that we can use to mitigate the synchronous problem. Okay, have we then solved the problem? Yes, we've definitely solved something by using actors and futures, or JMS or whatever. You have an application that can utilize your hardware much better. But if you only have one thing and that one thing fails, then you're screwed, right? So we need to also do something else. And that something else is called reactive systems. The Reactive Manifesto. How many of you have signed the Reactive Manifesto? Okay, so 25%. It's on reactivemanifesto.org. I only have 4 slides, so I'm quickly going to cover these 4 traits. It consists of the 4 traits: responsive, resilient, elastic, and message-driven. And if you already know, you can look at the beautiful picture and just zoom out for a while. Responsive is the topmost trait. And what do we mean when by a system being responsive? It's quick to react to all users under blue skies and gray skies. You have to always ensure a positive user experience, regardless of, load on system, time of day, day of year, Black Friday, and so on. Today's users are very spoiled. If the page does not reply, or if they don't get any response within a second, they'll go somewhere else, probably to your competition. And a colleague of mine, Duncan, he says, it doesn't matter what your system does under the hood if it's not responsive. So this is the uppermost trait. So a trait below that, how can we build this responsive system, is to make it resilient. And most applications, at least when I was a consultant, they were designed and developed for blue skies, the happy path, if you will. But things will go wrong. We know that, right? So a resilient system applies proper design and architecture principles to ensure responsiveness even under gray skies. And resiliency tend today to be one of the weakest links that we find out there when we do consulting. The next trait is elastic. And I think elasticity and resiliency go hand in hand to create this performance system. An elastic system is easily scaled out, but it should also be scaled down. This was actually, the trait was called being scalable initially, scalability, but that kind of gives you the idea that you should only be able to scale out. Now, when we go to the cloud today, it's of course important to create a system that can scale down, because that's also going to save you money. And also, you want to be able to scale up and down, so you want to utilize the hardware that you have on your machine. So your machines shouldn't be idling around 30%. Of course, they should be utilizing the CPU that's available. And finally, and I'm really proud of this picture too, don't try this at home, kids, but it's message-driven. Using a message-driven approach correctly will enable your applications to be both asynchronous and distributed. So this is key for being elastic. Of course, being from Lightbend, I think you should be using Akka actors to build these type of systems because they will give you all of the 4 traits out of the box. So you're welcome. So we now know how to build these reactive applications. They should be responsive, elastic, resilient, and message-driven. So that was a quick overview of the reactive part of my talk. Now I'm going to move on to microservices. I don't know how many times I've seen systems like this. This is a system design overview, if you wonder, or an architecture overview. Of course, in most cases, this is completely unintentional. But you know, getting new requirements, you build something, and then someone else comes with new requirements, and you add it on, and all of a sudden you're in this mess, right? What happens when we end up in this mess? Well, there have been a couple of new inventions. 10 years ago, the brightest shining star on the sky was SOA, service-oriented architecture, which is now considered a bad word by many. I think that's because the tooling was really poor, and people went way overboard with various standards like BPEL, BPML, SOAP, of course, our darling, OASIS. There was even an acronym called OMG, which doesn't stand for oh my God, it's Object Management Group, and so on and so forth. So we were forced to use all of these standards. And as engineers, what do we do when we get overloaded with frameworks and standards? Well, we reinvent the wheel to a less complicated situation. We went from EDI to XML to JSON. The problem still exists, it's just a new way of approaching it. We went from RUP to XP Agile to Scrum, Lean, Kanban. We went from spaghetti soup to APIs to SOA and now to microservices. So we're trying to solve this by just inventing something that we consider new, but the problems still are there. So jumping headfirst into microsystems could leave you in this place. So we're basically ending up in the same place that we try to move away from. However, the only difference is before we were on one machine, now we're spread out over a massive amount of machines. So this is actually a worse place to be than we try to get away from. So you really need to think long and hard when you're developing microservice. And there are a couple of core recipes, if you will, that you can apply. One of them is isolate everything. I'm sure you've heard of bulkheading. Don't let errors spread inside of your application. Use graceful degradation. I normally give Netflix as an example. Their core service is to stream video, right? But they also, the landing page is recommendations. These are two different services. The streaming service is super important, The recommendation service, well, it doesn't really matter. As long as you can look, watch the video, you don't care about the recommendation page. So therefore, they need to use bulkheading. So if the recommendation service has a problem, that should not affect the streaming service, right? While I'm talking about Netflix, if you have Netflix and haven't checked out Better Call Saul, then you should. It's a great, great series. The next thing you should do is do one thing and do it well. Here you should think the Unix philosophy, single purpose, well-defined responsibility, and composable. So that's what you want to aim for your service. The service should definitely own its own state. So use the API or APIs to call into the data that the service owns. I was consulting for a large Nordic bank 12 years ago, 13 years ago, and we were going to replace their mutual fund system. Their mutual fund system was running on a mainframe, and they had a DB1 in there. And the DB1, I don't know if you've done mainframe development, but if you're in that mainframe, you can call wherever you want, right? So all the dependent services, they were calling into the database. They were just selecting data from the database directly, which basically means we had no clue how many dependent systems there were in the system we were going to replace by a J2EE service. So you have to make sure that there's only one way of accessing the own state. There are other reasons for this, but I would say, at least you have an idea of what dependencies you have. And finally, embrace asynchronous message passing, play nicely, and don't take any thread hostages. There are lots and lots of other recipes that I'm not going to go through. There are 2 booklets that we have. My 2 colleagues, Jonas and Marcus, have written, so they are free if you go to lightbend.com, resources, ebooks. You can download them there. Okay, so let's now we know reactive, we know microservices, so let's move on to monitoring. So monitoring has been around quite some time. So we have synchronous systems, and synchronous systems are fairly easy to monitor. You have entry and exit points because there's a request and there's going to be a response, so you can start a timer. And based on that timer, you stop that timer when the request goes out, and you can deduct all sorts of metrics. There's also the benefit of there will be a stack trace inside of this synchronous application. So, if service A calls service B, that's going to be in the same stack trace. So if service B blows up, you'll get a chain of events that led up to where the exception happened. You can also and that also means that logs are more descriptive. You can also use thread locals to pass context in this environment. And MDC is a well-known framework to use that. And like I said, monitoring of synchronous systems have been around for ages. There are many good systems out there. So if you're building synchronous applications, you should just hook one of those up. However, since we agreed that the new way to build systems is to make them reactive and also use distributed systems, microservices, that means that we introduce a whole lot of problems when it comes to monitoring. So let's move on to monitoring asynchronous systems. And this here, how many have seen this before? Yeah, it's very hard. So this is a stack trace, an asynchronous stack trace from inside of Akka. So basically, we have a demo in Cinnamon that's called failure demo because we need to trigger failures so we can see that our monitoring tools are working. But the first line there, it's failure demo Scala line 102. The rest is Akka and fork join related. So it doesn't really tell you anything of what happened. Of course, and it's executing on different threads unless your framework is using just one thread, which Node.js does, but Akka uses multiple threads. And you can look at the line, yes, and you can even look at the code, of course. Go to the source code and say line 02, what happened? The thing is, it's very hard to understand what happened, even looking at the source code, because there could be multiple events that have triggered this, right? You don't have any real good sense for what led up to this exception. So what we must do is train our dog or dogs Instead of getting caught in the thread fence like dog number 1 does, we need to train it to jump over this fence and also teach it to carry context, which it's holding in its mouth there. So that's what we need to be able to monitor asynchronous systems. And I'm going to tell you how we do it, and that's by learning to play the piano. It's by using instrumentation. This was the best picture I could come up with. So what we do is we instrument Akka code to create these metrics. What does that mean? Well, when you start your system, we ask you to add a Java agent, please. And that's going to look at this Akka source code, and it's going to put point cuts into the Akka source code in particular places. And those point cuts are going to call out to an SPI that we have created, and that SPI is then creating these metrics behind the scenes. So let's look at what the SPI looks like. Here's an example. This is the abstract class actor instrumentation. And you can see there are a couple of, this is Scala code here, but we have a method called system started, and we pass in the actor system that was just started. We have a system shutdown. We have an actor started, actor stopped, and then we have 3 important methods. We have actor told, which is when you send a message from one actor to another. So we pass in the actor that's sending, we pass in the message, and we pass in the sender. And then we have actor received, and that's when an actor starts to processing a message. And then we have actor completed, and that's when the actor has finished processing this message. So whatever is going on inside of, we have lots and lots of more methods that we call in this SPI, but these are the core ones for Akka. And what's happening then? Let's look at the sausage factory, if we can. So inside the sausage factory, this is actually from inside Akka code. Now, the bold text here is what we instrument in. So, you know, Akka doesn't look like this if you look at the source code. We add this in runtime to Akka. And then we have, this is inside the method invoke, and that's going to be called by Akka when there should be a message process inside of an actor. And then we called the SPI method actor received with this actor, with the message, with the sender of the message, and also if there's a context. And then we do this message, or Akka calls this message handle message. That is going to call your receive method. So that's where your logic is executing. And then when you're done, okay, we know you've now processed this message, so we call actor completed. And based on that, we can create a whole lot of metrics. And this works really well for asynchronous systems. However, most of the time you have distributed system, right? And then it doesn't work, because then you're bound inside of JVM. That's what we do. So we need to also apply distributed tracing. And distributed tracing basically is, for each occurrence that happens inside of your system, you create an event, and you persist those events somewhere, some back-end system. And then you have processes analyzing these events, kind of combining them together to figure out what's going on inside of your system. And you also need to ensure that you transfer context at these remote boundaries. So now the dog not only needs to be able to jump this fence, it should also be able to jump into the neighbor or whatever. You know, between nodes, you need to transfer this context. So I'm going to quickly talk a little bit about football. This is football, everyone. I'm from Sweden, so in Europe, and the rest of the world we call it football. And the idea here is to pass this ball around. So for my colleagues, and the assignment is when we receive the ball, we already have written our name on the note. And when we receive it, we write when we received it, and then when we pass it on to someone else, we write down the time, right? So I received the ball first, 4:22:23, and I passed it on 4:22:29. And then you can see in the times here, Peter received it 4:22:32, passed it on 4:22:40, and so on and so forth. So if we take these notes now and put them in a box, and then we tell someone, you know, can you just order these notes and line them up, then it's going to look something like this. So I received 422.23, passed it on 422.29, and Peter received 422.32, and so on. So this seems to be right, but there is, of course, something wrong with this, since I asked a question like this. And that is, time is not the same everywhere. You know, I'm using my clock. Peter maybe looked at the wall in his room and wrote down the time, and I don't think those clocks are synchronized. So the problem is time does not, when you leave your node or your machine, time will be different. So there are two approaches to solving this problem. The picture to the left there is something called NIST F1. It's a cesium fountain clock. It's in the National Institute of Standards and Technology in Boulder, Colorado. So this is the primary time frequency standard in the US. And in 2013, the uncertainty of this clock was plus minus 1 second over 100 million years. So that's pretty accurate. I think we can live with that, at least for now. And the funny thing is, it says in 2013, so they will calibrate this going forward, so it's just going to get better. So a well-known company called Google are using this for their databases today, and that database is called F1. I don't think that's an accident, you know. So they're using that as an acronym for the database. And this basically means that they can use ACID transactions distributed over their system. And the reason for this, I know everyone loves event sourcing at this conference. I happen to be one of those that we must embrace both these paradigms, especially if we want all engineers to get on this bandwagon. One way is using Google F1. Of course, that's only for Google. And they specifically developed F1 because they thought event sourcing was too hard for their engineers to grasp. That kind of gives you an idea of the domain. There's also an open source database called CockroachDB. That uses similar functionality to Google. It's three ex-Googlers who've started this project. And I think this is really interesting. There will most likely be more of these types of databases that gives you ACID, but in a distributed environment. So I think that's interesting. The other way we can approach this is to be dapper. And what I mean by that is that Google released a paper in 2010 called Dapper, where it's what made causal relationships popular. It's not Google's invention, but they kind of made it popular. And that's how they did distributed tracing in their environment. So basically what you do with Dapper, or what Dapper paper told you to do, is to keep track of a trace ID, a parent ID, and a current ID. And based on these three, we can connect them causally. So we're going to apply this to our paper note experience, or experiment. So you can see we've now added a trace ID, and the trace ID will be the same for all of these. It's the same trace. And then what we've introduced as well is parent ID, and then our unique ID, which is the name. And looking at these nodes now, if we look at the one down left corner, there is no parent ID. Okay, that kind of tells us that this must be the first one, right? Because it's not pointing back to anything. And then, if you remember in the old example, my note was first, Henrik's note was first, and Peter's was second. But using this approach, we can immediately tell that, well, actually, Peter's note is first because it's not pointing to any parent. And looking at my note there, it's actually got parent ID Peter. So it's pointing back to Peter. So if we align these now, we can get, I wouldn't call it true time because Google uses that as well, but it's like this is the order when things happened. So Peter is first, and then my note is next, then Björn, then Duncan. Right, so distributed tracing, not only you can order things, but it also tells you stories about your architecture. Because if you keep on tracing like this, you can build a map over your systems. And this is really important when you're dealing with microservices, again, because you can understand how important the services are and where you should put your focus, because I'm thinking of service design as an onion, and the core bit of the onion is the most important thing. And then you have layers on top. You know, everything is dependent on the core. So that's what you should really that's where the SLA should be the best. Okay, so distributed tracing, not only you can order things, it also gives you an overview of what's happening in your system. Perfect, right? The only problem with distributed tracing is that you have to create this instrumentation yourself, right? So if you are running Spring and Hibernate and PostgreSQL and Kafka and stuff like that, you need to make sure that the context is propagated between these tools. So it's basically been broken unless you've been wanting to invest in all of these tools and kind of git clone them and add your own code to them. So it's been broken more or less until this year when open tracing was announced. And this is a vendor-neutral open standard for distributed tracing. And it supports 9 languages up until date. Some supported tracer implementations are Zipkin, Jaeger, Lightstep, and Instana. And basically, this is a synchronous system we're dealing with, but you can easily apply this to asynchronous systems, and we actually do it in Cinnamon. So we do open tracing integration. But it will give you an overview, a timeline like this. And if there's time, I'll show you Zipkin, our Zipkin example, where you can see how things are related to each other and also when they happen in time. So basically, you can get these answers from distributed tracing. What parts of the architecture is slow, potential candidates for parallel calls, forensic material for failing situations, and traces for auditing and debugging and stuff like that, and also this map of how the systems are related together. So, okay, so we now know how to do it for asynchronous systems and distributed systems. But of course, there are challenges, and there are also mitigations. So the first challenge that we've seen a lot is how to handle scale. Let's say you have a cluster or many clusters, and you have, let's say, millions of actors running in there, and you're creating traces for everything, and you're creating metrics for everything. This will be the equivalent of drinking from a fire hose. The first approach I was involved in, called TypeSafe Console, we actually tried to create events for everything. And we ended up having customers waiting 6 minutes for the data to being crunched before they saw the metrics popping up in the UI. So we realized this is not a way forward. And so we're using a different approach this time around, of course. So the mitigation for handling scale, there are a couple of things you can do. One thing is to provide a configuration so that the users themselves can define what parts of the actors or their application they want to monitor. There might be parts of it that's not as important. There might be parts that generate a lot of traffic, and then you can exclude those if you have a good configuration provided. You can also implement dynamic configuration, looking in at runtime, having some external thing, deciding what parts of your system should be monitored, and instruct it to create more metrics or less metrics. Another thing is to introduce sampling. So you're not tracing every call, you're tracing every 1,000 call or something in your system. And you can also attach counters to events. There's a company out there called Overops, former Takipi, and they do exactly this. They're watching what's happening in the JVM. If there's an exception, then they will log it, and they will attach a counter. And for each new exception that happens in the JVM, they'll just up the counter. So basically, you can see, okay, this exception has now happened 150 times. Instead of logging all of these 150 times, they just up the counter, which is, of course, much cheaper. And also, you can gather metrics closer to the source. And what do I mean by that? In monitoring, there are 2 paradigms, ruling paradigms today. One is push and one is pull. So the most famous one, or one of the most famous ones, is for pushing is stats-D. Basically, you have your monitoring system just pushing all the metrics somewhere else and then expecting a server to be able to cope with this load. The other one is pull, and the most famous one there is Prometheus, and that's part of Kubernetes, for those of you who use that. And that's basically scraping data from the source. So you store it locally, and then Prometheus will The Prometheus will come and take the data at once. And that also means that you can decide what parts of the data you're interested in. So you don't have to, and then it's like a tree building up. So you have a top node that can get information from all these underlying nodes. Another problem with monitoring or issue is ephemerality. So this here is an imprint, a foot imprint, not a person, of course. And when the wave comes crashing in, then these footprints are going to be erased. So these are ephemeral. But you can keep track of all sorts of information to determine, for example, how many people have walked down this beach by counting the number of footsteps. And you can also look at individual footsteps, so you can keep track of how many different people have walked down the beach. You can see if there was an exceptional occurrence, so someone stepped on a sharp rock, jumped to the side, things like that. So, and this is something we see happening in the world today, is things are coming and going much faster, right? So before we had the mainframe, that's not going to move anywhere, so that's always there. And then we went to JVM maps, and then we went to microservices, and then we had actors, futures, and function as a service even now. You want to tag these as the same thing. You know, if a node falls over in a cluster and it spawns somewhere else, then that's actually the same thing. It's just started in a new physical location, but the metrics are still the same for that. So the mitigation for this is you should try to find these patterns of metrics instead of looking at individual instances. And one thing we do in Cinnamon is that we provide you to group actors as on class instead of instance. So you can gather metrics for this actor class, regardless of how many instances there are, they will all be grouped in one place. So 1 million instances, you will actually just track one piece of metric associated with that actor. Another challenge is staying cost effective, and cost effective, by that I mean both in time. There will always be overhead when you do monitoring. There's no such thing as having the cake and eat it too, right? So there will be a penalty in time. And the thing here is to minimize, of course, the overhead. And that's up to us, but that's also a little bit up to you, what parts of your system that you decide to monitor. And also another thing related to this is money. Yes, it's becoming cheaper and cheaper to run stuff, so you create more services. Those services will generate more data, which basically means you have to handle more data. So it's like you need to make sure that you can handle this in an effective way. And again, giving a monitoring tool which you can decide what parts you want to monitor, and also having dynamic configuration. So you can, this zooming in, zooming out the functionality is the way to mitigate. Another thing that we see a lot is correlation. So let's say we're looking at the metric message process for an actor, and then all of a sudden we see a drop, right? So something's going on. It's very hard to determine what is going on because, of course, there could be a garbage collection going on, and that's going to affect this metric going down. There could also be an issue with the network. So on the operating system level, there could be a planned downing, so you need to hook into your orchestration tool. And there could be a data center issue. So all of these actually come to play. You can't just look at one bit of information. You need all of this together. So mitigation of this is to combine a lot of sources and have them available in the dashboard at the same time, so you easily can get an overview. Oh, look, there's a drop here, but there's also a garbage collection going on. So that's perfectly normal. Or the DevOps guys actually planned this node going down, so we don't have to wake the developers up. And I think a lot of companies here are looking at machine learning and training these algorithms to actually be able to deduct this information automatically. So you don't have to have this dashboard, but someone will just call you. Probably Siri will call you at 3 a.m. Okay. Another thing that we're struggling with when it comes to monitoring is, of these types of systems is that the variety of them. They're just like snowflakes. There are no two similar systems I've seen. They're always implemented in different approaches. Akka is great, but it also gives you, it's a very powerful tool, which basically means you can do whatever you want with it, right? So some companies, they use a lot of temporary actors that are created, 10,000 actors per second, short-lived, 50 milliseconds. Other companies, they have these long-living actors that run forever. Of course, monitoring these two systems will have a different impact on the back end. So again, configuration is a really important thing, and the zooming in, zooming out functionality. The problem with zooming in, zooming out is that if a system is struggling and your algorithm or you realize that I need more information, something's going on here, that could actually push the system over the cliff, right? Because you're requesting more data when it's already struggling. So there's a thin line there what you should do. The last challenge that I'm addressing here is higher availability. How good is your monitoring system if it falls over when your system falls over? You can't deduct anything, right? So you actually have to make sure that your monitoring system has higher availability than the system it should monitor. Otherwise, you could end up in situations where your system falls over, your monitoring system falls over, and you have no clue what happened. And the mitigation of this, of course, is to apply the Reactive Manifesto to your monitoring system. So basically, you have all these 4 traits on your monitoring system as well. And by doing that, then hopefully, you will have higher availability of your monitoring system. So those were some challenges and mitigations for them. I'm now going to peek quickly into the future. It's actually no longer the future, it's already here. But looking at some deployment trends, I've mentioned this before, but we went from mainframes to mini computers to Unix servers to Windows on x86 and then Linux on x86. And this was, of course, introduced by Google and Amazon when they started this cloud computing thing. That it became cloud computing, and then based on that, we now have serverless and function as a service. That's been around for around 3 years. And I'm quickly going to talk about function as a service, or serverless, or no-ops. It has a lot of names. Basically, for Amazon Lambda, short-lived functions. They're triggered by events. They're fully stateless. They have auto-scaling, so you don't have to take care of anything. They're just going to scale out. And you pay per millisecond of invocation. There was a really good talk earlier today about how to apply Amazon Lambdas and build reactive systems. The problem with this is that the simpler the service, the more complex the operations. So if you're trying to implement something similar in your domain, then you're going to have a hard time understanding how this system works. Amazon has therefore developed something called X-Ray, which gives you really good insight. I was impressed by that tool earlier today as well. Okay, so let's take a quick example of what Lambda could look like. This is Node.js, and it's just a hello world example. Node.js, JavaScript, it returns a string. And looking at that, this thing can execute at some random time, at some random server. And looking at that paradigm, and then comparing to actors, actors are fully location transparent, which basically means you don't know where they're going to execute, right? They are going to react to a message. So in that sense, they're quite similar to Lambdas. We need to keep track of things, of course, and I'm going to get to that later, how we can do that. But actors and Lambdas are quite similar. We also have something called futures. And futures are an anonymous block of code executed some point in time, somewhere. Hopefully on the server you have the code running, of course. But so this is not really new, Amazon Lambda. All it does is it's emphasizing a monitoring need that already exists. And that's a good segue to our solution called Lightband Telemetry, also known as Cinnamon. So the current feature list that we have is that we create metrics and events and traces for Akka actors, remoting and clustering. We also do this for Scala futures, dispatches and thread pools, and Akka HTTP, which was recently added. We provide MDC propagation over asynchronous boundaries, but also remote boundaries. So if you have an MDC, Cinnamon will carry that over inside of Akka, but also over remote boundaries, if you call remote nodes. So if you have clustering, it's just going to take that MDC and keep going. As I mentioned earlier, we have open tracing integration, and we integrate with various backend integrations. Ops Clarity, which is our own, but we also have plugins for other things that you guys maybe want to use. So we have plugins for Elasticsearch, StatsD, Datadog, and so on. And actually, I'm going to show you a screenshot of the Datadog dashboard. So basically, if you're a Datadog customer, all you do is you download Cinnamon, and you configure it, and you use the Datadog integration, and you give it your Datadog ID, and we have provided this dashboard for you, so you can just take this dashboard in Datadog, and you'll see your application data streaming into that. A couple of upcoming features. We are going to provide you with Play26 metrics, events, and tracing. Play26 is based on Akka HTTP, and we already have Akka HTTP support, so it's not a big thing for us to add a Play26. Play25, we haven't discussed that yet, but it might become, we might put it on the roadmap as well, but Play26 for sure. We're also going to provide instrumentation of Akka streams, instrumentation of Akka persistence. We're going to provide Prometheus integration, and we're also super interested in hearing, getting feedback from you. What features would you like to have in Cinnamon? So I'm here, and my colleagues in the team, Peter and Björn, are here, so feel free to come up to the stage after and talk to us about Cinnamon. I'm going to quickly show you a demo. So what I have here is I'm running a couple of Docker instances. So we're going to run Zipkin, and we're also going to run Kibana and Elasticsearch. And I'm going to start with Cinnamon Visceral, which is our new project. And this is going to be created as a Docker image. All you have to do is run a Docker image. Now I'm running everything locally, and Visceral is a Node.js application. I also need to start a sample application, so I'm going to do that. So basically what this is doing is we have a sample application generating data that's being pushed into Elasticsearch, and then we have a service that's retrieving this data from Elasticsearch, creating JSON from that and pushing that over a WebSocket out to Node.js, and Node.js is then this view here. So now the WebSocket connection is going to be established, and then all of a sudden we have data. This is perhaps not very visible, but this is, it says local, and this is the actor system that you're seeing. So we started actor system. So if I were to run a clustered system or a remote system with multiple nodes in it, you would see all the nodes, and you would also see the connection between nodes. And then I can see all the actors that are running in this node, and I can jump into it. Visceral has a small bug, so and sometimes it actually draws all the nodes, or actors in this case, over one spot. So if I enable dragging in physics, then I can make this look really cool, actually. So let's turn off physics. Okay, so now I can just drag these. And the cool thing about this is a dummy, or just a demo example. But what's happening here is, so we have messages flowing back and forth, and you can also see there are some yellow dots, right? And they're going to a node called dead letters. So basically, you can just highlight this dead letter actor, and all of a sudden you'll see what actors inside of your system that are creating dead letters. And I think this is a really good starting point. It gives you a sense of how the messages are being sent inside of your actor system, and you can also easily identify where there are issues. We also have, not in this demo, but if there are errors, like exceptions or some log errors, they will create red dots. And if you have remote nodes, so you have a clustered system, you are going to see the nodes on the side here, so the remote nodes, and they are sending into your local actors. And you can also see if they are causing exceptions. On the node level, the same thing. If there are exceptions going on, you'll see red dots and yellow dots between the multiple nodes. So, and this is something we're working on right now, so I don't have a better demo than this, but this is going to be downloadable, so you can apply this to your own system and just try it out. The next thing I wanted to do, I'm just going to shut down a couple of services here. So the next thing I wanted to do was to run another sample app, or actually 3 different instances. And localhost, foo. All right, so let's see if this works. Of course it didn't work. Okay, there we go, demo gods. But basically I wanted to show you that we have a Zipkin integration. So what I suggest, let's go back to look at this beautiful image. What I suggest, I mean, this is a good approach to how you would drill down into your system. You can easily identify, of course, you know, there's some dead letters here, but by going into Zipkin, you can see individual traces, right? So you can see the faulty exceptions for individual traces. And then if you run Kibana, you can search Kibana in Elasticsearch. You can look for the individual trace, and you can get information about the message that was sent, the actor that was sending, what actor it was trying to send to, and stuff like that. So this is the overview, and then you can look at individual traces, and then you can move on to the details of it. And then we provide Grafana dashboards for metrics and stuff like that. But unfortunately, I'm out of time. So with that, and as I said, feel free to come up here and discuss Cinnamon or monitoring in general, if you will. Thank you, guys.